We learned in the previous videos how to advertise and call ROS services to achieve sequential execution of a software functionality. Also, in a broader sense, ROS services are our first step towards event-based execution of software functionality. That is, we acquire and process information only when needed. However, blocking executions may not always be desirable. Let's take a look at a case for non-blocking execution. Imagine we are in the process of analyzing an existing process at a factory production line where we have a robot arm and a mobile robot working together. Let's now take a look at what they are programmed to do individually. The robot arm picks up an object while the mobile robot remains idle. The robot arm places the object on the idle mobile robot. Then, the mobile robot delivers the object at a specific location while the robot arm remains idle. Then, while the robot arm continues to remain idle, the mobile robot goes back to the same location as earlier, and then the object pick and place cycle repeats. So, only one of the two robots is moving at any given time. Perhaps it is still wise to keep the robot arm idle and wait for the mobile robot to successfully deliver the object to its destination. But it is not efficient to keep the robot idle while the robot is navigating back for the next pickup. We can perhaps be more efficient by already having the robot arm pick up the next object while the mobile robot is still navigating, like we see here. However, if the motion executions of each robot is implemented using ROS services, this would not be possible, as we always have to wait for the navigation to finish before we can start moving the robot arm. So, is it possible to do this at all with ROS? Yes. Enter the scene, ROS actions. With ROS actions, there is no waiting needed until the completion of an execution of a set of commands. In other words, ROS actions are non-blocking, and if it is really required to wait until execution, actions can be configured to do so. Further, ROS actions provide a more generalized request-response mechanism compared to ROS services via a client-server communication. We also used client-server terminology with services, but we will soon see how ROS actions are different. In ROS actions, the request field is called the goal, the response field is called the result, and a new field, feedback, which provides a continuous feedback related to processing the goal request. For example, the feedback message could comprise of the current position of a mobile robot with respect to its desired goal position. Let's now look at a simple example of an action definition. Our requirement is to have a ROS node that counts up to a specified number of counts with 1 second delay between each count. So, our goal request message is an unsigned integer specifying the number to count up to. The result message contains a string on successful completion of counting up to the desired number, and the feedback message that tells us how many counts have elapsed since we started our counter. So, we create the action file counterwithdelay.action. Then, we specify the goal request message field. Then, the result message field. And finally, the feedback message field. And of course, let's remember those 3 little dashes that differentiate the different message fields in a ROS action definition. Great. Let's now quickly see where we put the action files in our ROS workspace and some utility commands. ROS action definitions also reside in the ROS package where project-specific messages are defined, and naturally in the action folder. ROS action messages can be automatically generated by putting the action definitions in the CMake lists file as we did with services. However, we can also manually generate action messages after creating them. We can do so by running the command rosrun actionlib_msgs genaction.py path to action file. This command generates a set of action message definitions, and we will look into these in more detail in the next video. And of course, after the messages have been generated, we can use the ROS message show command to display the contents of the action message on the terminal screen. Now that we know how to define a ROS action and where these definitions reside on the ROS file system, let's have a look at what types of functions are available to process an action goal request. The goal callback function can be used to run the computations after receiving an action goal request. Note that a goal request can also be preempted and cancelled before attaining the goal. Discussing these aspects of goal preemption is, however, beyond the scope of this course. Additionally, a goal can be in different states while being processed. For example, a goal currently being processed is in the active state, or a goal that was achieved is set to succeeded state, and so on. There are also additional states, but they will not be required in this course. In case you are interested, you can have a look at this link. As the last topic for this video, let's get acquainted with the code nomenclature used in the context of ROS actions, similar to ROS services. An action server ROS node. This node advertises an action and starts the corresponding action server. This lets other ROS nodes to request action goals to be processed. Then we have an action client ROS node. This node is used to send the action goal requests to the server for processing. ROS actions are extremely useful in designing intelligent and clean robot software applications. At the same time, they are also a bit more involved than the services and topics we saw earlier. So, before looking at code example, let's dig a little deeper into the world of ROS actions in the next video.